Hey Ben, I'm not gonna lie, I have not done BC calculus in a really long time, like 15 years. So I'm gonna do the best I can with this here for you, and it may or may not be super helpful for you, but I've been looking at this for the last little bit, and yeah, I can see things could be a little challenging. So, I guess I was gonna start with the tests, like the ratio test and the root test. So if your limit is less than 1, the series converges. And if L is greater than 1, it's divergent, or it diverges. And if L equals 1, the limit fails. So the test is inconclusive. All right, so the ratio test, I just picked two really easy examples, if I can find where I did. I have all these notes that I was doing. Okay, so the ratio test basically says that you find the limit as k approaches infinity of a of k plus 1 divided by a of k. So for whatever your example might be, so here's our example. If I give you the series k equals 1 to infinity of 1 over k factorial, and I want to use the ratio test to see if this converges or diverges, we say the limit as k approaches infinity, and then we're going to do 1 over k plus 1, because we have to add 1, divided by our original, which is 1 over k factorial. So multiply by the reciprocal, 1 over k plus 1 factorial times k factorial over 1. And hopefully you know that this reduces to 1 over k plus 1. So we end up with the limit as k approaches infinity of 1 over k plus 1. And as we plug in infinity, 1 divided by numbers that get bigger and bigger and bigger, this limit will go to 0. So this converges by the ratio test. Okay? So for the ratio test, the rules are going to be the same for the root test as well, if L is less than 1 or L is greater than 1. But for the ratio test, you're just adding 1, in this case, to k. Sometimes it's n, sometimes it's x, whatever variable you're using. I bet you use n a lot. So you take your original function, add 1 to whatever you need to, and then divide it by the original function. Simplify, take the limit, and you get that. All right, I'm going to switch colors. So then the root test, just for another basic example, I said find if this converges or diverges. 4n to the 4th plus 58 over 5, sorry, I had to find my example, n to the 4th minus 3n cubed all to the n power. And let's say we're going n equals 0 to infinity. Okay, so the root test says you just take the square root of everything. So you're going to square root the whole thing, and then you're going to find the limit as n approaches infinity. So we would have 4n to the 4th plus 58 over 5n to the 4th minus 3n cubed to the nth power. And then we want to take the square root of that whole thing, so that's to the 1 over n. Or we want to take the nth root, not the square root, but the nth root. And that's really nice because this cancels. Then you're just left with the limit as n approaches infinity of 4n to the 4th plus 58 over 5n to the 4th minus 3n cubed. And I can't remember whatever the name of the rule is, but if you have equal powers here, the limit approaches the coefficients. So we should just have that equaling 4/5. And so the limit as n approaches infinity is 4/5, which is less than 1. So this series converges. All right, so you have two different options. You have the ratio test, which is where you add 1 to whatever you need in terms of what the variable is you're working with, or you have the root test. The root test is probably easier often if you can use it. So I would go with that if it's a possibility, but those are just two very basic examples. Hopefully that will help you do some of your examples or be able to follow the solutions in your own examples. As for Taylor series, I went back and reviewed this. It was just so entertaining. Okay, so Taylor series, you have this. I'm going to change back to red because it shows up better. All right, so Taylor series. So you have this weird general formula, right? N equals 0 to infinity, f to the n times a over n factorial times x minus a to the n. And this is about x equals a. And a lot of the ones you're seeing are about x equals 0. And if it is about x equals 0, it's a Maclaurin series. I don't know how you spell it, but and so you may have heard of that too. But basically, the Taylor series, like this test, basically tells you if I have a graph of, I don't know, let's say, that's not a good example. I'm just trying to go off the top of my head here. Let's say I have a cosine graph that goes, on, and I want to know what happens as it approaches 0. I'm looking for a function that's going to model this in a similar way, right? So I'm looking like that's a graph of a quadratic. So I'm looking basically for an overall formula that's going to model the original graph by taking several derivatives to get closer and closer to what it should be. So that's basically what a Taylor series is. In terms of, I guess we can look at, I don't know, you had a lot of examples and I did a bunch of them out. I was looking for, I mean, let's just take one at the very beginning. You had cosine of 4x. I think it was one of the first ones. And so at n equals 0, which is your original function, f of x equals cosine of 4x, your original function, and that evaluated at 0, cosine of 0 is 1. Whoops. Sorry. All right, so then at your first derivative, which is n equals 1, you do f prime of x. The derivative of cosine is negative sine 4x, and f prime of 0 is 0. Sine of 0 is 0. At your second derivative, you're doing f double prime. Derivative of negative sine is negative cosine 4x, and the second derivative at 0 is negative 1. So you're going to see a pattern with sine and cosine. You do the third derivative, you get sine of 4x, you evaluate it, the third term at 0, and you get 0, and then you do the fourth term and things start to repeat. So you're back to cosine 4x, and you're back to where you started. So you have this alternating pattern. So when you look at this in terms of f to the n equals cosine of 4x, when n equals 0, 1, 2, 3, meaning the first derivative, second derivative, etc., you get this formula of, f of 0 plus f prime of 0x plus f double prime of 0 x squared over 2 factorial plus f triple prime of 0 x cubed over 3 factorial, etc. f to the fourth prime of 0 x to the fourth over 4 factorial. So in our case, we have 1, because our original function up here evaluated as 1, and then we end up with 0 for the second term, so we would have 0x, and then minus 1 over 2 factorial x squared plus 0x cubed plus 1 over 4 factorial x to the fourth. So every other term in this series is going to be insignificant. So you only need even powers. All right, so we just need the 1 over 1 minus 1 over 2 factorial x squared, and then plus 1 over 4 factorial x to the 4th, minus 1 over 6 factorial x to the 6th, plus 1 over 8 factorial x to the 8th. That is going to be our pattern with alternating signs. So the tricky part is actually finding the formula, and that is just some trial and error, and you kind of have to mess around with that. But, you know, it is n equals 0 to infinity. This -1 to the n is because you have alternating signs, so that's how you write the alternating signs. We're looking at 4x, which is our function, to the 2n, because we're only looking at the even functions. So 2 times 1, 2 times 2, 2 times 3, that gives us each even function. And down here, again, same thing, 2n factorial, and that's because we're looking at just the even powers. Okay, and if we were to simplify that, we get the sum as n equals 0 to infinity of -1 to the n, and then 4 squared is 16 x to the 2n over 2n factorial. So I just simplified this. 4 to the 2 is 16, 4 squared is 16, and then x to the n. So this is what your answer looks like. It's not overly pretty, but that's what it looks like. I did another one, and I'll do it out for you, and you can see if you can follow it, but this is about as good as I can do on short notice, and it's a whole lot of material that you're looking at. So I took this example, and there's someone at my door, so you're gonna have to hold on. Actually, I'm gonna keep recording. Hey guys! Oh. I'm making math videos. Thank you. Okay, thank you, thank you. Okay, sorry, no way to pause the video in this program that I'm using. So anyway, if your original function is f of x equals ln about x equals 0, so this is the Maclaurin series, so you do the same thing. Every time you have one of these, go ahead and write out your steps. That will for sure help, and you will get some credit. So like your original function at 0 is just natural log of 3. Then you do your first derivative, so f prime of x. Derivative of a natural log is 1 over the function times the derivative of the function. All right, so if we were to simplify that, we'd get 4 times 3 plus 4x to the -1. And then if we put in 0, and you can plug it in here if it's easier, you get 4/3. Okay? And if I do the second derivative, I'm going to go from this simplified form because it's much easier. You just use the power rule. Bring down the -1, so you get -4, 3 plus 4x to the -2 times 4. So if we simplify that, we end up with -4 squared, 3 plus 4x to the -2. And if you want to find the second derivative at 0, you plug that in and you happen to get -16 over 9. So you're going to keep doing that, and then the problem becomes, just so you know, the third derivative ends up being 32, 3 plus 4x to the -3 times 4, and simplifying this just for our pattern, that becomes 64 times 2, 3 plus 4x to the -3, which becomes 4 cubed times 2 times 3 plus 4x to the -3. Okay, and if you think about this, this right here, we've got 4, this right here is 4 squared, then we'll have 4 cubed. So then you're going to have 4 to the 4th. That's where you're looking for your patterns to see if that will help you at all. But what you basically have to think about is you're alternating signs, but you're alternating signs in a different way in this case. Because you're starting with a negative. And then you've got -1 to the n plus 1, 4 to the n minus 1 factorial times 3 plus 4x to the -n. So you're looking at each piece. This was the 4 to the first, 4 to the second, 4 to the third. But the thing that we don't use is the natural log of 3, which was our original piece up here, because that's just a constant. So that can go to the front when you do this. And then you end up with your -1 to the n plus 1. And if you look at these terms, 4/3, -16/9, your value here would be 64 over 27. You're basically getting 4/3 raised to the n power, and then you've got your n minus 1 factorial x to the n, and then you're dividing by n factorial. Now, you don't need to do all those steps, but in the end, this simplifies -1 to the n plus 1, 4/3 to the n, x to the n over n. It's definitely challenging. I mean, getting this formula is so hard, but hopefully, like, if you can follow each step here, then, you know, and definitely do each step, show this, and then look for patterns in terms of powers, because that's the power series, the Taylor series. You're going to be looking for all these exponential powers. You're going to be looking, does my sign alternate? Do I start with a negative or do I start with a positive? Is there a constant term I can put in the front? What's happening each time I went, you know, my power here is going from -1 to -2 to -3. The next one would be -4, hence this value up here. So there's ways to simplify it. Leaving it in this form would have been fine as well, and not simplifying it to this bottom form. I think any answer would be acceptable. But in a nutshell, that's about all I can do. I'm not even sure if that's going to be helpful for you or not, but write everything out. Write those steps out, because it's all about the derivatives at whatever point you're going around. Normally you're going around x equals 0. If you weren't going around x equals 0, you would just take whatever's here, and then instead of plugging in 0, you'd be plugging in 3 or 4 or whatever number you were dealing with. And as far as convergence or divergence, you basically need to just remember these rules, and if you can take the root test or the ratio test, if you can pick, I'd go with the root test if it's an option, because it's much easier, but the ratio test always works nicely. So hope that helps you a little bit. Let me know.